Welcome to the group exhibit Hydrogen, Fuel Cells and Batteries at the Hanover Fair 2017. We are here at the Technical Forum and my name is Muriel Burkas. I would like to also welcome all our guests watching the live streaming online. Please have a seat, join us for some coffee, some refreshments. It's all on the house. I would like to welcome the next presentation regarding novel power electronics for distributed generation and energy storage. Please welcome with me on stage Head of Product Development of Combined Energies, John Vogel.
Thank you very much. Hi, good afternoon. I'm John Vogel. I'm Head of Product Development for Combined Energies. I am a mechanical engineer by trade, so I'm extremely limited in the level of detail that I can get into with the actual operation of the power electronics, but I hope to be able to answer all of your questions at the end of this program. You're welcome to come visit us in booth C36/2 at the Northeast Electrochemical and Energy Storage Cluster, and I'd like to thank Paul Aresta for being able to set us up so that we could exhibit here today. As a company, Combined Energies is a startup company located in Latham, New York. We are focused on micro combined heat and power and distributed generation. And in our past lives, in the decade plus that we've had in developing and fielding microgeneration systems, we've identified several critical barriers that we think that have held back micro CHP from widespread distribution and commercial uptake. One of the main ones of that is the power electronics. We feel that the power electronics that are commercially available are unsuitable for micro CHP, and we decided to try to tackle this problem. I'd also like to thank NYSERDA, the New York State Energy Research and Development Authority, New York STEP, and the U.S. Commercial Services, from which we received the grant to be able to be here this week. So Marathon LR, our motivation behind this was after years of searching for appropriate low-cost power electronics to be able to take the variable low-voltage DC output of a fuel cell and convert that into the rock-solid, set-point, high-voltage DC required by most commercial inverter stages, we couldn't find one. So we did a fairly extensive literature and product search, and we wanted to come up with something that was that had efficient conversion to AC with commercially available inverter stages, also cost-effective DC power transfer within the system. So, for example, we had in mind large SOFC or energy storage systems on a utility scale, with these devices outputting high amperage onto bus bars and triple-aught cable and that sort of thing. If you did conversion at the source of generation, you'd be able to reduce the cost and complexity of that transmission within the system. The increased life of power generation, so as a fuel cell's life decays and the voltage decays, our experience is that the power electronics would be incapable of handling the power produced by the fuel cell well before the fuel cell was actually at end of life. So we believe we could greatly extend the life of a fuel cell using our DC-to-DC converter. This would also give you system architecture alternatives. So, for example, we see situations where people are putting 300 cells together, 600 cells together, and able to increase the output voltage. This would allow you to be able to go where the chemistry or the device wants to operate and be able to boost that up onto a high voltage bus, so it would give you architecture advantages. And increased useful energy production. So, for example, ultracapacitors. I have a chart here that we took data on later in the presentation, where it shows that actually ultracapacitors have a limited ability for us to be able to extract the useful energy from that, simply because the voltage decays to a point where we can't use it. And we think the same is for other distributed generation devices. I have a list of other technologies that we believe benefit from this high DC boost. We started with CHP systems. We've talked to a lot of people about range extenders and flow batteries. We had a discussion with other people at the show today that there might be a significant problem with solar use with PEM electrolyzers, that there is a incompatibility with power electronics there that we think we could help with. Some of my European colleagues suggested we try to use this with a coal-fired power plant. I didn't think that would work very well, but we said we'd look into it. And so our solution was, after an extensive search, we found a topology which is readily available, which is it's a MOSFET-based, very high current friendly DC boost topology, which didn't give us what we needed. So we combined it with an isolation stage, and that would allow us to give an additional boost to what we needed. What we wound up with was a 10-to-1, greater than 10-to-1 DC power boost ratio, and very high efficiency at low voltages. An odd thing in this topology is that as you decrease the input voltage, the actual conversion efficiency increases slightly. So we found that to be advantageous. We found that we could extend the life of energy conversion. This is a very robust topology, lends itself very well to conformal coating. It doesn't require any external cooling, there's no fans, and it operates in a very robust, dusty, potentially caustic environment. The variable degree of isolation is a subtle point that we're digging into right now. We want to push the actual National Electric Code galvanic isolation requirements onto the AC stage for distributed generation. We do not want to do that on the DC stage. However, we do have the ability to provide isolation if needed by the application. So in a variety, if you're looking at DC bus or DC microgrids or something, you could go all the way to very robust toroidal transformers that'll give you robust isolation, or you could go all the way to very low cost, cost-effective planar transformers on board that wouldn't give a lot of isolation, but could be useful in filtering and in your design for EMI requirements. Again, we talked about design latitude for low voltage, and then the ability to extract additional energy from ultracapacitors. And I might add that our topology is bidirectional. So you could either operate in a unidirectional phase, as we would with distributed generation, or it could be bidirectional and it can buck down from high voltages to low in the case of recharging batteries or ultracapacitors. How it works is we have 3 stages on our board. We have an input stage that's broken down into phases. These phases are interleaved. The input stage works as spreads the current across the stages from your source and acts as DC to AC inverters, which is then boosted in a transformer stage. The number of turns ratios will define what the boost is. We found that in avoiding bus bars, the ability to be able to transport the current on board without the use of things like bus bars, we're limited to about a 7-to-1 boost. Because of the interleaved nature of the different legs, you get an effective doubling of that. So we get just under about a 15-to-1 boost ratio from this topology. The output stage then is broken down into single-phase rectifiers, and the controller concentrates on the inner loops, controlling the switching of the input stages and the output stages, and then the outer loops reduces it to a very workable, very manageable, seemingly simple device that can work with either the inverter, outboard power electronics, or then go out onto a main controller out onto a DC bus. An application here would be our near and dear to our hearts, distributed generation. You look, you see we have everything here. We have a fuel cell, we have batteries and photovoltaic panels. The DC to DC converter, while it could be close coupled with the inverter stage in one unit, would act to interface with the fuel cell, and the high voltage batteries. It would be bidirectional when you're charging the batteries. bringing everything up to a high voltage bus that could be integrated with the photovoltaic panels and go into the inverter. Another application that we're demonstrating right now in hybrid electric vehicle systems, as these vehicle drives go from 80 volts to 300 volts to 600 volts, the bus demands are outstripping where the energy storage and especially the power storage can go. So in the application that we're testing right now, you have a medium voltage battery as the energy source on a ground support vehicle. Then the ultra caps are a 48 volt ultra cap that the DC to DC is bringing up to the bus voltage. And of course that's bidirectional, so you can charge through regenerative braking, you can recharge the ultra caps. The last one is one we've begun to explore. Again, we're thinking about the solid oxide or large utility scale energy storage and placing one of these cards integral with an individual stack. We think that can do two things. One, it allows you the opportunity to have larger active area, lower cell count stacks, and also be able to get rid of your bus bars and your heavy cabling when you're transporting everything out of 400 volt or 600 volt bus out to your inverter stage. Where we're at right now is we have several different versions of our prototypes under test in various conditions. We're a small startup company, so we're working with a manufacturing contracting house in Rochester, New York. We're here today in order to be able to gather commercial requirements. We're looking out and trying to overlay as many requirements as possible in order to produce a market entry product. We envision producing maybe 100 of these, getting them out to OEMs and to end users, and be able to collect the detailed requirements back from the different markets. We think there's a much different market segments in energy storage than there is for flow batteries, than there is for off-grid, so we would envision a portfolio of products that would be able to be tailored to each one of these markets' needs. Do you have any questions?
Thank you very much. First one. Thank you. Questions for John? No? Okay, I just have a question. Your early stage startup,
yes.
Still.
Yep.
Would you say you are influenced right now by having a new president in the US that is maybe not so much in favor of renewable energy, or there's lots of rumors going on, but because you also got funding to get here and stuff like that?
I don't see that at all. I don't see the funding being diminished, and I see a lot of the stuff that was R&D based and government funded being driven down into the private sector. So I think it's a time of opportunity.
Great. I'm glad to hear that.
All right.
Thank you very much. If you have further questions or want to discuss the topic or collaborations later on, please go to booth number 36, right in the back behind the technical forum. Thank you very much for your time.
Thank you.
So I know it's lunchtime, and I appreciate it even more if you stay with us over lunchtime. The upcoming presentation will start in about 5 minutes at 12 regarding the topic hydrogen and the transport sector, future options for e-mobility in Germany. I am very much looking forward to this presentation held by Dr. Katrin Goldammer. Thank you.